Welcome to Summarize Science. Today, we're diving into the strange world of extremal black holes. These aren't your everyday black holes. They're theoretical objects pushed to the absolute limit of physics, with the maximum possible charge or spin for their size. They're so extreme they have zero temperature and sit on the boundary between a black hole and a naked singularity, something most physicists believe shouldn't exist. But a recent paper asks a crucial question. Could these perfect, extremal black holes actually persist in our universe? First, let's consider an electrically charged black hole. You can think of it like a giant, cosmic battery, and just like a battery, it wants to discharge its energy. The researchers show that this happens in two incredibly effective ways. The black hole's immense electric field is so strong it can literally rip pairs of particles out of the empty vacuum of space, a process that neutralizes its charge. But even more powerfully, any stray hydrogen gas nearby, which is the most common element in the universe, would be instantly ionized, zapping the black hole's charge away. For a black hole to be massive enough to prevent this ionization, the paper calculates it would need to have a mass of over 100 trillion suns. That is fantastically larger than any black hole ever observed, making electrically extremal black holes practically impossible. Okay, what about magnetic black holes? These would get their charge from hypothetical particles called magnetic monopoles, which are like magnets with only a north or a south pole. The paper finds that for a magnetic black hole to be stable against instabilities, it would need to have absorbed an enormous number of these monopoles, somewhere between 1 million and 100 million of them. This plot here shows how that instability behaves. As a black hole gets more extreme, meaning its mass gets closer to its charge, the instability grows stronger, threatening to tear it apart. The biggest problem is that creating a black hole with such a huge magnetic charge is cosmologically implausible. It would have had to form in the chaotic first moments of the universe, and the odds of that specific outcome are vanishingly small. Finally, we have the most realistic candidates, rotating black holes. We know that astrophysical black holes can spin incredibly fast, some getting very close to their maximum possible speed. But could they ever stay perfectly extremal? The authors suggest a fascinating and previously overlooked idea. They argue that the constant hum of the gravitational wave background, a sea of ripples in space-time from countless cosmic events, would interact with the black hole. This interaction would gently steal its angular momentum, acting like a cosmic brake that prevents it from ever maintaining a perfect, extremal spin. So, let's recap the key takeaways from this research. Electrically charged extremal black holes would be neutralized almost instantly by the matter and vacuum around them. Magnetically charged ones would require an impossibly high charge and are unbelievably unlikely to have ever formed. And even the fastest spinning black holes are likely being subtly slowed down by the ever-present background of gravitational waves. The conclusion is a powerful one. The universe itself seems to have built-in mechanisms that prevent these perfect mathematical objects from existing in reality. While this means we'll probably never find a truly extremal black hole, studying objects that get very close to this limit could still be a fantastic way to test the laws of quantum gravity.